We're going to dive down a completely different rabbit hole here with Lakshmi. So, Lakshmi, welcome.
Hi.
Would you like to tell us who you are and what you do here at Datrium?
Sure. I'm Lakshmi Bairavasundaram. I'm a member of technical staff at Datrium, and I work in the file systems and snapshots team.
Great, but it's not even file systems and snapshots we're looking at. This is a really interesting area that I've been hearing people talking about a lot of recently, and it's looking at some of the actual science and statistics around failure, and particularly the poorly understood partial failures that go on in disk systems. So you guys have written a white paper about this and some of the statistical analysis.
I've worked on partial disk failures for a while. That was my PhD topic, so it's like sort of near and dear to my heart, and I monitor the more recent publications in the area and where the work is headed towards mitigating the effects of partial disk failures. As a way of introducing partial disk failures, the fact is that drives fail in general, and enterprise storage systems have to protect customer data by handling these drive failures. People have had various ways of handling drive failures over the years. The main work in the area was in the 80s, and this became more mainstream after the paper by Patterson and et al. And this was basically called RAID.
This was the original
This was
RAID
the original
paper.
RAID paper, and it was titled "Redundant Array of Inexpensive Drives," and it became independent drives
Because
later on.
the perception of what's inexpensive changed.
That's right, exactly. And so after that original work came out, people have built on top of that, and the original work had multiple RAID levels. And
we don't see a lot of RAID 3 being deployed.
Not quite. It wasn't as popular as the RAID 5 alternative. So what we have here is the next question. Sure, we have RAID, we can deal with disk failures.
And RAID was really about that switch from having a single disk that held your data to having 5 or 7 or 10 drives maybe.
That's right. Yeah, originally it used to be this really large drive that held all of your data. The RAID work really came up with an alternative way to store all of that data in such a way that it was both inexpensive and its reliability characteristics were as good as having a single drive. Because the fact is that if you have one drive and it has a certain failure probability, that could be pretty low. But when you have a large pool of drives, then the probability that any of them could fail is much higher than a single drive failure.
Yeah, approximately you sum the failure.
That's
right. So long as the failure probability is very low, you sum them then.
Exactly.
Yes.
So the RAID work came up with a way to store additional information that will allow you to recover data that you would lose if a single drive failed. And then now people have built on top of that. And so the next sort of question, now that you have RAID, you want to handle drive failures, the question becomes how many drive failures do you need to handle? And the current answer is at least 2 failures. And we are not the first to suggest this or look into this. NetApp had its RAID DP paper that came out in FAST more than 10 years ago. Now virtually all serious storage systems deploy 2 failure tolerance. That's as a standard option.
And the original rationale around that is that the rebuild process, when you've had a drive failure, you rebuild by basically populating a whole drive and reading everything from all of the other drives, and the probability of a failure during that activity was significantly higher than it was at any other time.
That's right, because rebuild times used to be larger. So the previous way people did RAID was to have one spare disk that you would reconstruct your data and rebuild your data and put that data into that single spare disk. So you are limited by the bandwidth that spare disk offers.
Fill time for that.
The fill time for that. And also you were limited by like how much you could read from all of the drives in the pool.
And also doing the rebuild of your data, because you had one parity set in there, so you had to do an XOR across the whole stripe in order to rebuild that data.
That's right. Now it's a little bit different, because now you have a larger pool of drives. There are declustered geometries available where to go into a little bit of jargon, your stripe width, which is the number of units that you put together to form a single stripe that you recover data from. So that stripe width is not the same as the size of the pool. So you spread your stripes across the entire pool so that you don't have to rely on a single drive or a single set of drives to rebuild your data.
What I still think about is distributed sparing as part of it, is that you have spare capacity in each drive for rebuild.
Instead of a spare disk drive, now you have spare capacity to rebuild across the entire pool. Again, you're writing to the whole pool instead of to one drive.
And again, you're not just working with 6 or 8 drives, you're now dealing with 120, 200 drives.
That's right.
And aggregate performance to rebuild is on those.
That's right. So rebuild times have become greatly shorter. Now the
probability of the full failure of another drive has reduced.
That's right. If you have like a 4-hour rebuild, then you have maybe a 2% chance that your drive fails in a single year. Then that 4-hour time window is too short for a second failure to happen. Or the probability is lower. And so now the question is, well, maybe it's good enough to have protection against just a single failure. But even 10 years ago, NetApp's paper noticed that that's not the only case that they wanted to deal with. They wanted to handle the case that there is a single drive failure and something called a latent sector error is found on one of the other drives used for the rebuild. And turns out that the probability of hitting a latent sector error even during that rebuild time is really high. And that's the reason that you need to protect against 2 failures instead of just 1 failure. And we'll go into what the details are as to what a latent sector error is. Sometimes latent sector errors are called bad sectors. This is the case where you read a sector from a disk drive and you're unable to read it. The disk drives have error correction codes, and they try to use the error correction codes, but they are not useful enough.
They're not deep enough error correction.
They're not deep enough error correction, and you're not able to read your data back. With disk drives, this used to be the case where sometimes there are stray particles that could cause scratches. There were things called high fly writes, which would make it so that you didn't write the data well in the first place, things like that. And that was the problem with disk drives. Now with the solid state drives, it turns out that you still have issues with latent sector errors, and they're called uncorrectable errors in the world of SSDs, but they do tend to happen.
So still, no matter what storage media you're using, a single copy of your data on that storage media is not guaranteed to come back.
That's right.
At least it sounds like you're fairly sure if it has. So there's the difference between unreadable and reading corrupt as well.
Yes, and there are cases where you could get corrupt data back. So it's important that when you build your storage system, you build it with additional integrity mechanisms at the higher layer, and preferably end-to-end mechanisms, so that every layer of the system can be like handled if there are any issues.
A defense in depth strategy of protecting.
Yeah. That's right. So people should be using checksums. People should be verifying something known as referential integrity, where you check to make sure that the data you're reading is something that belongs to what you're reading it for, essentially. Yeah. So that's something that many storage systems are now built with, and we certainly recommend it. And
this is the academic. We recommend it. Datrium does this all the time. Yes.
Yes, Datrium does this all the time. Yes, we have end-to-end checksumming and referential integrity. We verify it.
Or just didn't want any confusion on
yeah,
that one.
Yeah. So we, from an academic standpoint, we recommend for anybody building a storage system that they put in these mechanisms, but Datrium does it.
Yeah.
So sort of switching back to latent sector errors, it's called latent because it's hidden. Essentially, if a drive fails, you would be notified that the drive has failed. Usually there are things that detect the drive failures. But when a sector simply dies, there is no notification mechanism that, hey, the sector has died. And it's found only when you actually read the sector.
Data access, and sometimes it's referred to as bit rot.
Yeah, that's right. Sometimes it's referred to as bit rot. So there are mechanisms both within disk drives and outside of those disk drives that sort of constantly scrub the drives and make sure that, if there is some latent error, then that error is discovered.
And it's discovered before there's an error condition.
That's right.
Yeah.
But you can't scrub in some sense. You can scrub at a fast enough rate to keep all of the errors away, to eliminate errors. And it'll amount to reading every sector all the time, and that's not quite going to happen. We've looked at data that was published by NetApp. It was a study that I worked on while I was an intern there, so I'm quite familiar with it. The sort of the key result that we saw was that around 8.5% of the disk drives developed latent sector errors in 2 years. This was for the kind of drives that are the enterprise SATA drives that are prevalently used in storage systems.
Large storage systems.
Large storage systems. It also turned out that when a single drive has a latent sector error, it didn't stop at one. It had many more, and a lot of those errors developed within a 1 month time frame.
So it was a rapid degradation.
That's right.
Right. And then you couldn't, because it was affecting a large area within the same drive, nothing inside that drive is going to be able to reliably protect you.
That's right. That's right. There was some spatial locality, so you could argue that maybe we could have some mechanisms within the drive, but there was also enough spread that you could say, well, you probably
the probability
is pretty high, so you shouldn't trust it. So that's the sort of the detail on what latent sector errors are and sort of how often they occur. So now the question is, how do they factor into the RAID math for reliability? So the original discussion when we had 2 full failures was a second full failure happening during that rebuild window.
Yeah.
Now the equation changes a little bit because latent sector errors don't just happen within that rebuild window.
Yeah.
They could happen earlier, and if you don't discover it before the first failure happens, then they've been there all along. And now you will discover it when you're trying to read the data back to rebuild.
And even if you're doing a periodic scrubbing, you may only have scrubbed that sector 4 weeks ago.
That's right.
And so a whole bunch of errors may have turned up on adjacent sectors then.
That's right. So what we did was to figure out what are the chances that you would lose data if you had only single fault tolerance, which is tolerating the first drive failure and nothing else. There the math becomes very interesting. So we factored in a reasonable rate of scrubbing. A lot of systems do. We can say for sure that every system does. Datrium certainly does drive scrubbing. So we had some reasonable assumptions. Let's say a pool of 30 drives. Many storage systems have many more drives, much larger. So we figured this is a reasonable starting point. And the data loss probability we find increases with the number of drives. So this is a sort of good conservative estimate.
The rate of scrubbing probably decreases with the number of drives as well, because you simply don't get more time.
That's right. That's right. We assumed that the storage system scrubs every single sector on every drive in a 1-month time frame. So on average, it is about 15 days since you last looked at a sector. And so if you think about the 8.5% number over 2 years, then you can like sort of cut it down to a 15-day number as to what is the probability that one of your drives.
1/24 of that.
That's right. And
the bucket math says you're now at about 8% chance.
That's right.
8 or 10% chance during that rebuild.
Yep.
Wow.
Now that you have the sort of the conditional probability of this happening, then you plug in the probability that a drive fails in the first place. And then you multiply it with the conditional probability that there is this latent sector error that's discovered during rebuild. Once we do that, we find that in a 1-year time frame, the probability is around 0.5%. Which, if you think about it in terms of the nines of reliability, is less than 3 nines. So it's sort of between 2 and 3 nines.
And that's over any 1 year. That's the percentage chance that a particular 30 drive system will experience data loss.
That's right. It's data
loss
as
a result of a disk failure and a latent sector fault.
That's right.
That's scary.
Yes, and it's not. The system's lifetime doesn't stop at a year, so it's usually around 4 years, we could say. And the approximate math is to just multiply by 4. The actual is a little bit.
It gets a little higher over time, I would expect.
Yeah. And so it's about 2%.
Yeah.
Which is which is scary.
Yeah, particularly for somebody who maybe has half a dozen or a dozen disk systems, then you're starting to say, well, because they're independent failures, they're just going to sum.
That's right. It's scary.
Yeah.
And when people ask about like, well, did we actually run into this? We haven't heard of a case that this has actually happened. There are various important things to consider. The first important thing is that the drives may not have been there for a long enough period of time. So we've seen that age is not good for the quality of.
So that bathtub curve through the middle lifespan of the hard drive, they're usually pretty reliable.
Sort of. For latent sector errors, we didn't quite see the bathtub effect.
But then the wholesale failure,
the whole thing, the probability actually increased with time.
Right.
So if you have 2-year-old drives, then the chances are going to be much higher.
But the probability of the drive failure that's going to expose data loss due to the latent sector error follows the bathtub.
Yeah, so it definitely relates to... it's a little complicated because first drive failure is going to be based on the bathtub curve, but the second one, not quite. But
it does suggest that there's a really toxic time for your disk system when it gets to sort of 7-8 years of age.
It's true, but it could even happen earlier. 7-8 is definitely like you're really having a risky sort of situation. But we'd say like 3 to 4 years, like this could be pretty bad.
This is where the latent sector rate's going to be climbing.
Yep.
And of course, if you have a latent sector error that's detected due to an I/O rather than due to scrubbing, you can rebuild using the parity data that you've stored.
Right.
So
that's right. So the normal like single failure mechanisms work well in that case, perhaps really well, because you have only one sector that you've lost at that time, you rebuild and you move on. So it's good to do scrubbing, and that greatly reduces the probability of data loss, but not quite enough. And
it doesn't remove it.
Doesn't remove it.
Yeah.
So
the other thing is the latent sector errors may also include other systems may not actually. There may be silent data corruption going on due to those latent sector errors rather than failures of the rebuild.
Yeah, so when you encounter a latent sector error during rebuild, what does your system do? If you have a system that protects against 2 failures, then you have a different mechanism to do the rebuild so that you don't have to rely on the piece of data that you lost to the latent sector.
And you've got another set of parity to verify that the parity you've just read or the data you've just read is valid.
That's right. But if you do have the data sector array for single fault tolerant cases, then you wouldn't be able to recover it. So you have to do something with this sector. The ideal case would be to report data loss to the customer, but we're not sure that the system would do that. Sometimes these layers are built independent of each other. So if there is no end-to-end data integrity, where we can't quite be sure that the RAID layer did the right thing during rebuild.
Yeah.
And that's going to be the...
And this may be a factor in why we don't actually observe reports of failed rebuilds. Is that just whatever the last data that was successfully read gets returned, and now your data is corrupt.
That's right. And if the data belongs to some important snapshot, you will probably run into it when you're trying to recover from it. If the data belongs to something that causes your Windows to blue screen, then you probably assume it's Microsoft's fault. You don't quite realize what's actually happened. And so it's important to have the end-to-end integrity to detect such cases as well.
And that's why the erasure coding that's in the Datrium is I can't remember what the spread was on it, but it's 2 copies.
That's right.
It's 2 item loss.
That's right. It tolerates 2 failures, and the important part is that when you go from tolerating 1 failure to tolerating 2 failures, you do have some additional overhead that you have to put in, like you have to use extra space. Now, if you're moving from something like RAID 5 to something like RAID 6, then your overhead is probably 10%.
And your I/O, your write I/O overhead, it's gone from a 4-to-1 multiplier to a 6-to-1.
That's right.
Your write performance sucks even worse.
That's right. So the question is, how do you do it efficiently? So if you have a log structured file system, then erasure coding is a natural, efficient fallout of that. So that way you are always writing full stripes, and therefore you do not have the performance penalties that you incur if you're writing 3 copies instead of 2. So this is both good for space and performance if you have erasure coding and a log structure file system on top of it.
Great. Well, I think we've run fairly long because, again, this is the stuff I really find interesting, is digging inside, thinking about the probabilities, and I particularly love analyzing failure modes because things aren't interesting when they're working right.
Yes.
But when things go wrong, you really learn, and also you find the character of the underlying system. So, Lakshmi, we talked about a white paper that you've written. Is that easy to find on the Datrium blog?
Yes. If you search on the website, you should find the paper on single failure tolerance. You can search for myth or fact, I believe, and you'd probably find that then too. We have both HTML and PDF versions.
Well, thank you very much, Lakshmi. It's
Thank you so
been
much.
great meeting you. And please do join us for more of the vBrownBag Build Day at Datrium videos. I'm Alastair Cook, and it's a great day here at Datrium.
Thank you, Alastair.